Hi, my name is Gérard Burnside. I'm going to talk to you about big data, graph and matrix, which is the work of Do Young and myself from the mathematics department in Bell Labs. So big data is really important today. It's important for our customers because we're trying to harness a huge amount of data and being able to make sense out of it. What we're going to talk about is about ranking information in a huge graph. Let's take an example with Google. When Google does a web search, what happens is that you get the results in milliseconds, even though there are billions of web pages. So how Google does that is that it processes the structure of the web pages offline, and it gets a score for every web page. And then when you do your research, it will sort the pages according to that score and give you the most relevant one on top. So what Google does to rank the pages, it does PageRank, which is trying to find the most important pages, which is determined by the fact that it's pointed to by other important pages. So the problem with that is that when you're trying to find this, if your page is important, you have to find if pages pointing to you are important, and you have to do that recursively forever. So luckily, mathematically, this is solved by the equation of the eigenvector x equal px, where x will be the solution that we're trying to find, with each coordinate being the rank of the page, and p is the matrix representing the web pages. Here's an example of a graph which you transform into a matrix. Each time you have a link between a node here and another node, you will have a point in the matrix. Here you have a point here, meaning that the web page I points to the web page J. And this equation, x equal px, how is it solved? One common way to do it is to do a power iteration iterative method, which means that you start with a value of x, you multiply it by the matrix p, and you keep doing that, you iterate, until you find an approaching solution of your equation x equal px. So doing the multiplication that I just mentioned is like that. You have the matrix P, which represents your web graph, and you have your solution here that you're trying to improve by multiplying by the matrix. When you do the multiplication, you use the rows of the matrix. In terms of the graph, it's like using the incoming links of a node, which is kind of like the intuition of PageRank that says if your page is important, it's because it's pointed to by important pages. So you find that intuition back here. What we did is we chose a completely different approach. We used the columns of the matrix instead of the rows. And using the column of the matrix is like saying, I'm interested in the outgoing links of my nodes instead of the incoming links, which is kind of equivalent, because when you say, instead of collecting the score from your pages pointing to you, you're diffusing your score to the pages outside. And we have found that doing that method allows us to have strategies which make it much more efficient than actual methods. If you look on YouTube, you can find those videos here. This video here shows how exactly it works, how we do the diffusion mechanism, and how we gain at least a 10-time factor with the current existing method. Here we have a couple of videos which show how we can distribute the method, because thanks to our fluid diffusion, we don't have to be synchronous with each node in the cluster, so we can have a real complete distribution, very efficient. And here we applied our method to partial derivative equations for the heat diffusion. When we discretize that problem, we can actually use our method to solve this linear algebra problem. And we find that we can solve it 10,000 times faster than a Gauss-Seidel iterative method. Thank you.